Right, let's show that efficient algorithms can be simulated with circuits with only a small loss in the circuit size, namely time t can be simulated by Boolean circuits of size t log t. To remind you, we have two models of computation. We have the standard model of Turing machines on the left-hand side here. You have finite program telling the machine what to do, given what state it's in, which symbol it looks and scans on the tape, how to change the state, what to write instead of the symbol on the tape, and how to move the tape head one position to the right, one position to the left, and so forth. And at some point, after t steps of computation, a Turing machine, this algorithm is supposed to terminate with accepting or rejecting the input x. A circuit, on the other hand, simulating this machine will have to have the following behavior. It has a bunch of bits, x1 through xn, given as input to the circuit, and it has a bunch of logical gates, negations, ORs, ANDs, and it must produce the output of the computation in one of the gates, one of the nodes of the circuit, in the picture in the bottom one. It has to be 1 if the algorithm accepted the input x and 0 otherwise. And the size of the circuit is the number of gates. So I want to say that time t corresponds to size t log t. So more precisely, what we need to do is to show that we can transform Turing machine description to a circuit description in a way that the circuit size is t log t. So we want a transformation that will map an input length n to a circuit with n inputs, c, on x1 through xn, such that for any input z of length n, if machine v accepts that, the Turing machine accepts that, then the circuit must be 1 on the input z. How do we construct the circuit? So basically, we want to faithfully simulate the Turing machine. The only way to faithfully simulate the Turing machine that we know is to open up the Turing machine and see how the computation evolves over the t steps of the Turing machine's computation, and then try to simulate the Turing machine basically step by step with some circuitry. And as you shall see, the reason we can do such a transformation is because the computation of the Turing machine is very local. So let's look at the transcript of computation of our machine V on some input Z, where Z is a binary string of length n. So here I give you a snapshot of some time steps of the computation. The time goes from step 0, when we just begin the computation, to the next time step 1, time step 2, and so forth until the end time step t of n. And as you shall see, as you see in this first tape contents, we're starting in the initial state Q0. We're looking at the leftmost symbol of Z, which is 1. So we have Q1, Q0 looking at the symbol 1. And I put both the state and the symbol on the tape into 1. And I think of this as a generalized symbol of the generalized tape symbol. And then the rest of the tape contains symbols like 0, 1, 0, 1, and so forth. And let's say the machine's program is like this, which says that if I'm in state Q0 and I see 1, then I erase the symbol, keep my state to be Q0, and move to the right. And if I'm in Q0 and I see a 0, then I replace the 0 by a 2, change my state from Q0 to Q1, and still move right. And these two transitions are reflected in my description of the computation state at time 1 and time 2. You see I was in Q0, I was scanning a 1. According to my transition, I need to replace this 1 with a blank symbol, which happens here, and move 1 position to the right. So now my new tape symbol is Q0 followed by 0. And similar to the second step, I replace the 0 by 2, and again move to the right, and so forth. Okay, so how do we build a circuit out of this? One idea is to first do encoding of all the tape symbols, generalized tape symbols, as I mentioned, and everything can be coded in binary. So you assign bit strings of finite length to each generalized symbol on the tape. The strings that you need will be of constant bit size because the tape alphabet of my Turing machine is by definition some constant size. And the number of states on my Turing machine is by definition of constant size. So I only need constantly many bits to represent all of those things in binary. Okay, so I imagine that in each of these tape cells, I write down binary representation of the symbols in these cells. Okay, like so. And then I need to compute the value of the encodings of the symbols in the next time step, in time step 1, for example. What do I need to do? As usual, as you see in this picture, the only thing that changes are this part of the tape. So because I was looking here with my tape head, and that tape cell could have changed, and it did change in this case. And also my neighbor on the right changed. It went from symbol 0 to symbol Q00. Everything else stayed the same, so I could have just, left these things alone and only focus on this part of the tape which does change. So let's think about what we need to do in order to compute the description of the next tape, the symbols on the next tape in time step 1. If I need to know this symbol over here, then of course I need to know the symbol that is in the same position in the previous time step. And I may need to know the neighbor of that symbol on the left or the neighbor of that symbol on the right. So all I need to know is this triple of symbols in order to determine the symbol down, one symbol down. And I can compute how this triple of symbols translate using the transition of my Turing machine and build a transformation that will map the encodings of 3 symbols into the encoding of 1 symbol. And I call this a circuit F. It's a transformation that takes as inputs 3 encodings of the 3 symbols at time step 0 and outputs down below the encoding of the symbol in the appropriate position, which here will be Q00. And the only thing you need to know in order to build such a circuit is that every Boolean, every function on n variables can be computed by a Boolean circuit of size at most 2 to the n. In this case, the circuit is multi-output circuit, but the number of outputs is not that big. And even though in general circuits can be exponentially big in terms of the input size, in our case, the input is of constant size because of the alphabet size being constant, number of states being constant in the Turing machine. So the circuit for computing this transformation F also will be, even though exponential and constant, but still at most constant in size. Okay, so the size of F is constant. That's great. Now, if I want to compute the symbol at this position over here, then I also need to plug in the same kind of circuit, like a copy of the same circuit that will compute the symbol in this position by looking at the appropriate triple of symbols in the previous time step. And in general, since I don't know, as the computation progresses, I don't know where the action is going to be happening, where my tape head is located, I'm forced to put a bunch of copies of the circuits like so in all positions for the symbols in the next time step. Okay, and if I put all of the circuits together and apply them to the encodings of symbols at time step 0, then I will collect at the bottom of this sequence of circuits F the encodings of the generalized tape symbols at time step 1. If I want to go from time step 1 to time step 2, I do the same thing, and I put a bunch of such transformations, such circuits in a row in one level below, like so. Okay, and I keep doing this until time step t, and then at the bottom I will collect the description of the last snapshot of the computation of my Turing machine, and I can just check if it reached accepting state or not, whether it should accept or not. Okay, so that's how I get a circuit for this Turing machine. And let's see what the size of the circuit is going to be. First of all, the number of steps is at most t of n. So the number of levels in this circuit that I'm building will be at most t. And the width of the circuit that I'm building is also going to be at most roughly t, big O of t of n, because in time t, my machine can only walk for at most t steps in one position and most t steps in another position. So I would be generous and say it will walk no more than 2t of n positions, for example. So the width is t, the depth is t, and each circuit F is of constant size, which gives me the complexity side of the whole circuit to be big O of t squared. And that's not what I promised. I promised you t log t. So how can we do better? Well, to do better, we need special kinds of Turing machines, which are called Oblivious Turing machines. What is an Oblivious Turing machine? It's a wonderful algorithm which hides, can obfuscate its behavior in some sense. What happens is for every input z of size n, the position of the tape head of the Turing machine is independent of a particular input z. It's only a function of the input length n, which means that if you look at the trajectory that the tape head of your Turing machine goes through during the computation on a given input of size n, it will be the exact same trajectory for any other input of the same input size n. Okay, so how does it help us? Well, let's go back and look at the transcript of the computation of an Oblivious Turing machine. And for simplicity of presentation, I'm only focusing on the case of one tape Oblivious Turing machine, which honestly doesn't exist. You need to have two tape Turing machine for that, as I'll mention in a moment. But it will just complicate my drawing. So let me just stick with the not completely truthful representation of an one-tape Oblivious Turing machine for this presentation. So here we know where we'll be scanning, which symbols we'll be scanning at every time step. And those positions are fixed. They're independent of a particular input. They're just a function of an input length n. So if I know that the action is going to be happening around these positions, then I only need to put the transformation f around the same positions. Okay, so the only thing that will change is this two positions here, and then these two positions over here. That's where the changes will be happening because my tape head is my tape head is moving to the right both of those times. So knowing where it's going to be, I know which two symbols on the tape I need to pay attention to and change. And so I can draw a transformation which transforms these two tape cell encodings to the new tape cell encodings, and I can do so using some new transformation, let me call it G. And then I have a copy of G for the next time step, and so forth. And when I don't have G, basically what I'm doing is I'm allowing just straight lines. Okay, so I just connect the output, the encodings at time step 0 with straight wires to the encodings of the symbols at time step 1. The symbols don't change, so I don't need to perform any computation, I just copy. And so I have a bunch of wires going down where no action is happening, no computation is happening, and where computation is happening, I have my circuit G of constant size because it depends only on 2 tape symbols. Okay, and so this is what's happening. So I have a circuit which is very sparse now. To go from time step 1 to time step 1, I need only one copy of G, and this G, as before, because it maps constant number of bits to constant number of bits, can be implemented in constant size. The size of the circuit for G is a constant. And how many such copies of G do I need? Well, at most T of n, because the length of the computation is T of n, and I do one copy of G per time step. So now my size of the overall circuit is at most constant, size of each G times T of n, as opposed to T square, because now the width is very small, very narrow. Okay, so basically we know where the action is happening, so we put the computation device just in those places, and those places are the same for all inputs of given length, so we're not losing any information, and we know that everywhere else we can just copy the information from one time step to the next time step without losing anything. And so this gives us a much better, much smaller circuit size. The only thing is that we need to start or transform our Turing machine into an oblivious one, and nobody's promised us an oblivious Turing machine to begin with. But fortunately, it can always be done. And this is a very old result from late 60s, early 70s by Pippinger, Fisher, and earlier work of Haney and Stearns, who've shown that every time T algorithm can be made into equivalent oblivious time T log T algorithm. More precisely, they show that if you start with any Turing machine that runs in time T of n, and the Turing machine may have some constant number K of tapes, 2, 3, 5, has an equivalent Turing machine that only has 2 tapes, and the running time of the new equivalent machine is T log T, and the new machine is oblivious one. So its trajectories of tape head positions are independent of the particular inputs and only a function of the input length. Okay, so this is an amazing result. This is a very interesting algorithm, and it's a construction. So you can take the description of the procedure from those papers and apply them to your particular Turing machine, which is not oblivious, and make it into an equivalent oblivious machine with only logarithmic factor loss in time complexity. Okay, I will not give this proof, just take it as given. The corollary of this is that we can now take our time T Turing machine computation, make it into oblivious 2-tape time T log T computation, and then given an oblivious machine of running time T log T, when we build a circuit from it, the way I described, the size of the circuit will be pretty much the same as the number of time steps of the new machine. The new machine has T log T time steps, so the size of the circuit is big O of T log T. And that's how we get that time T can be simulated by size T log T. One thing I didn't mention, and I don't want to spend too much on this, is the 2-tape Turing machine versus 1-tape Turing machine. The definition of Turing machine I gave you was, for simplicity, just 1 tape, and you have a finite control, the state, and you look at this tape. You can imagine several tapes like 2, and you scanning independently some positions on 2 of those tapes, And then based on the information in those two tapes, you decide what to do next, which means how you update the information in those locations on the two tapes, what new state you enter, and how you move independently on tape 1 and tape 2. So you can go left on one and right on the other, and so forth. And the construction for the circuit for two-tape machine follows the same structure as the one-tape construction that I described. You just have to imagine that you have another snapshot of computation of the Turing machine for the second tape, okay? And you kind of trace how that second tape evolves the same way as you traced how the first tape evolves. And when you compute this transformation G, you also need to know what was happening on the other tape, because the transition function of your Turing machine, the program of your Turing machine, depends on the information on both tapes. So this circuit's G will have as inputs the information coming from appropriate circuits G prime for the second tape, and similarly circuits for G prime will have to have as inputs some information coming from the circuits G for the second tape. But that's not very difficult. Conceptually, it's pretty straightforward to do. Okay, so that concludes the proof that time t can be simulated in size t log t. Now let's go back to proving the NP completeness of 3 SAT. So remember, I promised you that if you give me language L in non-deterministic time t, then I can build a 3CNF of size roughly t log t, such that the input is in the language if and only if the appropriate 3CNF, that is the output of my reduction of size t log t, is satisfiable. Okay, so let's see how we can do that. A given language L in non-deterministic time t means that I have a verifier that has input x and description of a witness y, where the length of y is t of the length of x, and the length of x, let's say, is n. And the run of the verifier is big O of t of n. So I have a deterministic algorithm running in time t of n. And what I want is to build the 3CNF. What I can do already, given the description of the transformation from algorithms to circuits that I've shown you earlier, is that for every input length n, we can efficiently, in polynomial time, construct a circuit C that will faithfully simulate my algorithm. In this case, it's algorithm V on inputs x and y. So I'll have a circuit which has inputs x and y, such that the algorithm V accepts if and only if the circuit outputs 1 on the inputs x and y, and the size of the circuit is small. It's going to be at most t log t from what we've shown earlier. Now it's very simple. So for every x, by the definition of L, we know that x is a yes instance of a language L, of a problem L, if and only if there exists a witness y that makes the verifier V on x and y accept. Since the circuit faithfully simulates the verifier, it's the same as there exists a y, such that the circuit C on inputs x and y outputs 1. And now let's define the circuit C sub x so that the inputs to the circuit C sub x are just bits in y. Okay, C sub x or y is defined as C of x and y. So I just take an x and hardwire into the circuit, and the only free variables left in my circuit C sub x are the y's. It follows that my circuit C sub x is satisfiable if and only if input x is in a language. And the size of the circuit C sub x, which is at most the size of the circuit C, is still at most t log t. Okay, so what we've shown is a reduction which maps an input x of length x to circuit C sub x of length t log t, such that x is in the language if and only if circuit C sub x is satisfiable. What does this show? It shows that the problem circuit SAT is NP complete. Okay, at least NP hard. So we get a reduction from any problem in NP to circuit satisfiability. Circuit satisfiability is, of course, the same as, very similar to 3 satisfiability, except that what we're given is not a 3CNF, but a circuit. So we're given the description of this graph with inputs and some gates, and we need to know if there exists an input to the circuit which makes the output gate say 1. So that circuit satisfiability problem. It's NNP because you can always guess an input to the circuit which makes it satisfied, and then evaluate the circuit in polynomial time in the size of the circuit. And the reduction shown just now proves the NP hardness part, that every problem in NP can be reduced to a circuit SAT. But that's not what we wanted, right? We wanted to show that 3 SAT is NP complete, Cook-Levin's theorem. That's easy to achieve now with a simple extra reduction, which maps circuit satisfiability to 3 SAT. So what we need to do, we need to take a circuit C, shown here, let's say on n inputs, and we need to output a 3CNF formula that I denote by phi sub c, with the property of the reduction C satisfiable if and only if the formula phi sub c is satisfiable. And like before, when we transform the Turing machine computation, the transcript of Turing machine computation into a circuit using locality of the computation of the Turing machine, here we use the locality of the computation of the circuit. Okay, so here's how we will do this. We'll basically introduce for each gate of the circuit a propositional variable. Okay, so we'll label each gate with some variable, let's say G1, G2, G3, G4, Gm-1, Gm. Here I'm thinking of m as the size of the circuit. And then we just need to say that these variables for the gates are assigned correctly given the assignment of variables that are inputs to those gates. So what I mean to say is, for example, that G1, which is the negation of x1, must be equivalent to not x1. G2 must be equivalent to G1 concatenated with x2, and so forth. And also we need to say that the last gate, Gm, is equivalent to 1. It's true. Okay? So now we need to impose these conditions over all gates on our circuit, which basically tells you that the value of the gate is correct given the values of the inputs to the gate, and you do this big conjunction over all gates in your circuit, and this will give you a formula which will be satisfiable. So the inputs to this formula will be both the variables x and the variables g, and the formula will be satisfiable if and only if there is a way to set the x's so that the values of the gates will be correct and the output gate will say 1. Okay. One small thing to worry about here is that it's not exactly 3CNF yet. I've written here conditions which look like equivalences, but those equivalences involve at most 3 variables each. Okay, the first one involves only 2 variables, the second one involves 3 variables, and the last one involves only 1 variable. So these are conditions on at most 3 variables. These are some Boolean conditions on at most 3 variables, some logical conditions. And anything on 3 variables you can equivalently express as a 3CNF in a fairly straightforward way. Okay, so each one of these conditions you can translate into an equivalent at most 3CNF. At most 3CNF means that the width of the clauses in your CNF is at most 3. And then you take the conjunctions of this at most 3CNFs and get a new at most 3CNF, which will be the output of the reduction from circuit SAT to 3 SAT. The size of this 3CNF that we get this way will be proportional to the number of gates in the circuit, because that's how many conditions we'll introduce, and then each condition will be replaced by a 3CNF of constant size. So the size of the 3CNF that you end up with is big O of the size of the circuit. The circuit was T log T, as you remember, when we did the translations from Turing machine computation of complexity T to a circuit, and now we transform that circuit into a CNF, a 3CNF of the same size, and that's how you get finally the conclusion that given n time T of n computation, you can get a 3CNF of size at most t log t, which is satisfiable if and only if input x of length n is in the language. One last side remark I need to make about this is that I talked about CNFs which have clauses of width at most 3, and then when I defined the problem 3SAT, those CNFs were assumed to have all clauses of size exactly 3. Okay, so that's not very difficult to fix now. If I have some clauses which have width smaller than 3, then I can always introduce some new fresh variable z added to the clause positively and negatively and replace a clause of size 2 with conjunction of two clauses of size 3. And this transformation can be easily seen to preserve satisfiability. The clause on the left is satisfiable if only if the conjunction of the two clauses on the right is satisfiable. And so I can always introduce some dummy variables and make my at most 3CNF into satisfiability equivalent exactly 3CNF. Okay, so to summarize, what we've shown is time t computation can be simulated by size t log t circuits. In particular, as a corollary, we get that polynomial time can be simulated by polynomial size circuits. What does it mean? It means that if we can show that problem 3SAT does not have polynomial size circuits, namely 3SAT cannot be done by polynomial size Boolean circuits, then obviously 3SAT cannot be done by polynomial time algorithms. So the circuit lower bound is much stronger than just showing that 3SAT is not in polynomial time. And this simple observation saying that circuit lower bounds is sufficient for proving that P is different from NP is a huge motivation for this whole area of circuit complexity that is actively pursued by complexity theorists. Our goal is to prove some strong circuit lower bound for a difficult problem like satisfiability. Our success has been pretty limited, to be generous. Okay, but we'll see some things that we can do and how it relates to algorithmic complexity of satisfiability in next videos.